Hey, so Eureka has these exponential word problems kind of all over the place, and has different approaches to them. We're going to approach them from a much more straightforward standpoint. And so we had to kind of gather stuff from all over the place that really matched the types of problems that we wanted you guys to do. So while we do start with lesson 26, we do wind up kind of meandering about the book a little bit for this one. So because what we want to show you is exponential word problems. Okay, word problems with exponential functions. How do you solve them? With logarithms. So check it out. If you just see a straight up interest problem, that's what these are for. These are for interest. Alright? If it just says, hey, you have an annual interest rate, blah, 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 you're going to use that one. Okay? If you see the word compounding, that's going to say that's going to trigger you to use this formula, okay? If you see the word continuous compounding, you're going to wind up using this formula. We're going to use all three right now, okay? So, first of all, we are going to look at A, which is asking us to compare something from example 1, which occurred previously in another lesson. So we're going to catch up. We're going to do the example 1 part right now. So example 1 and the other one. So I'm going to call this A sub 0, A naught, our starting point. So we're not doing A yet. We're doing the step before A. A0. Okay, so what if, so example 1 was this, okay? We're using the formula P of F of T, my bad, right? F of T equals P times 1 plus R to the T power. Okay, in this formula, okay, T is my principal. That's my starting amount, right? This is my interest rate. And this, of course, is time. Okay? So in the previous example, they were wanting to know how much money would you have if you put $800 in to an account that has a 0.03%, or sorry, a 3% interest rate, and I'll put 0.03 in there, for 2 years. You plug that into your calculator, and you get 800 plus 1.03 all to the second power. No, that ain't right. So I get $848.72. Okay? So that was what happened in example 1. Alright, so now we can do A. And now look, it's asking us to, instead of do what? Did I use the wrong interest rate? Okay, monthly. Okay, so this was compounded yearly. Okay, This question is worded really weird. So they're saying, hey, do you want to do this? Do you want to deposit your $800 in an account at a 3% interest rate compounded yearly, right? Which is that standard one. Or do you want to put it into one that is compounded monthly? Okay, so this is monthly compounding.
Are these like things that they give you?
Yeah, be really comfortable with them. Let me make sure I just wrote that right because I'm kind of trying to say, there we go. Yeah. Well, at least on examples of this that I've seen, like on the park exam, they give you the part. But be comfortable. Okay. So now we want to know how much money we would have. So P is 800. 1 is just 1. Our rate, it says, is going to be 2.976. We got to turn that into a decimal. 0.2976 divided by n. Okay, so now the newest thing is what n is. Okay, n is hashtag. Just kidding. The number.
Start writing that.
Of times it's compounded in a year. Hashtag of. That's a really popular hashtag. All right, so n is 12, right? If it's compounded monthly, then n is 12. And this is going to be 12 times 2. If I put that into my handy-dandy calculator, and at this point, guys, you don't have to show all the in-between steps. You got to show that you plugged all the numbers right in there. And then you got to put it in your calculator. 800. And actually, let me go ahead and get out my calculator so that you can see the way that I enter this. Okay, so here we go. I'm going to enter this into my calculator. I'm going to put 800 times 1 plus 0.02967. Is it 967? Please verify.
976.
Dang it. Divided by 12. And I'm going to close the parentheses and I'm going to raise that to the 12 times 2 or 24 power. And I get, if I'm going to round that to the hundredths place, because it's money, right?
Yeah.
Let's round it to the hundredths place. It's, huh? 12 times 2. It's in my formula over here. Right there. So it's n times t. T was the number of years, and it says for 2 years. All right. So for B, if we were to compare the total from part A, which one would you use? Well, you would use this one, right? Because you get a whole 28 cents more. Huh. 28 cents, I mean, that's 14 cents a year, dude. That's a lot. Okay. Hey, there's one more formula though. So let's do a different one. Let's compare which one is better. Let's go a sub 1. So we're going to do another a. What about continuous compounding? Continuous compounding is what we want to do. Continuous compounding, if it's alright with you. So for continuous compounding, we have the formula PERT.
Worse.
No. PERT. You haven't heard it since your mom was saying it? And P and R and T are the same thing. All right, so I'll plug stuff in here. 800 times e to the r, which is 0.02967 times 2. And I'll show you how I would plug that into my calculator. 800. And we're going to go times, I'm going to get my E button out, that's under ln. And it's e to the 0.02967. Dang it! Times 2. And I get $849.06. I got 6 more cents out of it. 849.06. What? Approximately 849.06. And obviously you would want to go with the interest rate that is going to be compounded more if you're getting money, right? If you're getting interest. All right. Now, the next type of problem that you can have with interest, so we got the 3 types of equations. The next type of problem you can have with interest rate is you might have to find out how long it takes to get, like, say, $1,000. So, how long will it take to get $1,000? Let's go ahead and solve using continuously compounding interest, okay? So in other words, I need to solve this. I'm going to have to solve for t. 800 e to the 0.029, is it 76? So then this is a typo? Or a write-out over there? Alright. And we don't know how long it's going to take, right? That's what we want to know. So our variable is t. We got to solve for t. Mr. T. Iced tea? Lemonade? Okay. First thing I gotta do is divide both sides by 800, okay? I'm gonna solve this thing. Divide, it's easy, so I get it.
It's easy.
They're underachievers. They're just going for the easiness. Wow. $800. Sorry, I didn't write that down. I divided both sides by 800. All right. Now I've got an exponential equation. I'm going to have to solve for t. How do I get t out of there? With logarithms. No. So I'm going to go ahead and take natural log of both sides because, right? Natural log is log base E. All right. Now I'm allowed to take that exponent out. Right? I can take the exponent out. Hey, what's natural log of E? Hey, natural log is log base E. Yeah, so what is log base E of E? 1. So all I have left is sorry, that should be a 0 there. I missed a 0. 0.2976 t. Boom! I can solve that in one more step. I will divide both sides by 0.02976. So my answer is natural log of 125 divided by 0.02976 equals t. I can plug that into my handy dandy. Yeah. Here we go. Ready? All right. So if we put that in our calculator, we get that t is approximately 7.5 really, right? If we're gonna round even to the 7.498 if we're gonna round to the thousands. But hey, we're trying to figure out how many years it takes, right? How many years? Technically, it happens during the 8th year, right? If you look at it, right? 7th year passed. During the 8th year, like halfway through the 8th year, you get your $1,000. So you would say it takes approximately. You say 7.5 years or approximately 8 years if you wanted to round. If your compounding continues, right? Okay, well, we are going to go ahead and move on. Yes.
Approximately 8 years, 7.
Because really it happens during the 8th year. You understand? You can round to 8.
So we can do like a larger understanding on this.
You can say 7.5.
Why do you say 8?
I want to know how many whole number years. I'm just answering in a whole number.
Okay. Yeah.
Okay. The next one that we're going to work on is on page 186. This is on 186. It's really weird. I told you we would jump around a little bit. So if you're looking for it, it's on 186. Okay. Chain emails. So think about this, okay? Number one, you hate these, don't you? Right? If you don't send this to 3 people, you don't love Jesus. You're like, but wait, I do. No. Hey, that's not nice. Yeah. You're like, wait, what? That's not cool. Anyhow, you can see how this thing grows, right? It's like a fractal that keeps going, right? One person sends it to 3 people, they send it to 3 people, they send it to 3 people, and it gets bigger and bigger. This is exponential growth, right? The 3 types of problems that we will be dealing with in this like 26, 27 section that we're doing are interest problems, which turn out to be exponential growth. Exponential growth problems involving like population growth and stuff like that, and bacterial growth, and then we'll also deal with exponential decay. Here we go with exponential growth. So, I want to talk a little bit about an exponential growth or decay. It is on page 186. So the way that these are going to look, is like this. We're going to have a final value, okay, is going to be equal to an initial value times our rate that it increases or decreases, and it's always going to be the sum. The exponent will be time. Okay? That's how those work. So here we go. If we have this e to the n, what's it saying? It's saying we start with 10 people, right? We start with 10 friends. Initially, 10 people have the email. All right? Each of those 10 send it to 3 people. Every day, right? Every day. And there it is. So if we wanted to figure out how many days it takes to send this email to 318 million people, we have to solve this equation. 318 million is going to be equal to, right? That's our final, right? We want to know that final. We start with 10 people. Each person sends it to 3 people per day. We got to solve for it. First thing I want to do is divide both sides by 10. If I divide this by 10, it's going to take it down 1 decimal place, pretty much, right? Now I have an exponent there. I would like to get rid of it. How do I get rid of it? I'll take the log of both sides. I'm going to choose log base 3 because I have a base of 3 right there. And I'm going to keep the million. All right. I'm going to pull the exponent out. Okay. Having a hard time writing. N, sorry, this is an N. What is log base 3 of 3? 1. So then I already know what N is, right? I'm going to go ahead and just write the step. I don't mind writing a little extra, it's okay. And now I'll put this into my calculator. I'm going to use my calculator because it has log base 3. If yours doesn't, change it to log base 10. But I'm going to go math, log base 3 of, I have my mind just blanked on what the number was. 31,800,000.
Yeah.
Right. And it looks like around 16 years. Or 15.724 years, okay? And is approximately 15.724.
Yeah. I got that. What you do wrong? Wasn't it days though?
Was it days?
Yeah.
Oh. So it takes 16 days. So. Okay. The next thing. Exponential decay. Which is a little bit nasty. Which we will look at next time. And this one is back on page 202. So we're back to. All right.